Hey guys! So today we're going to be talking about an action potential. And what an action potential is how neurons are going to communicate with other neurons or other bodily tissues, let's say a muscle for example, right? So the way that they're going to do this is electrically. And then after it's electrically, it's going to go to the terminal bouton and then it's going to secrete a neurotransmitter, which is the chemical aspect to this. So looking at the action potential, we're going to do this graphically. So right here, what I have drawn is the resting membrane potential. And what the resting membrane potential is that gradient that we were creating with those sodium-potassium pumps. Remember, we were pumping out 3 sodium for every 2 potassium we pumped in, this counter transport. So what that did was that created a negative potential inside the cell. Now, what we're going to do is we're going to have a threshold stimulus. And when we get that threshold stimulus, it's going to bring us up to what's known as threshold. Now, at threshold, something special happens. We have our voltage-gated sodium channels opening up and allowing a massive influx of sodium. Now, this is going to cause what's known as depolarization, right? And we're going to get all the way up to positive 20 to positive 40 millivolts. In this example, we're going to do positive 20 millivolts. Now, once we're up there, we're going to have our inactivation gate close. And what that's going to do is it's going to stop allowing the sodium to come in. Now, what I didn't tell you guys is also at this first threshold, we had the opening of voltage-gated potassium pumps. But the thing with the voltage-gated potassium pumps is they open pretty slowly. So now that we're all the way at the peak of depolarization, these voltage-gated potassium pumps have now fully opened. Now, what that's going to do for us is it's going to allow the potassium to rush out of the cell because we have a gradient of potassium. We have a greater concentration of the potassium intracellularly and a lower concentration extracellularly. So this is going to cause it to rush out. So what was positive is now going to become negative, resulting in repolarization of the cell. So we're going to come down, and then we're going to get to what's known as second threshold. What's special about second threshold is that the configuration of the voltage-gated sodium channel changes. So the activation gate is going to close, and the inactivation gate is going to open. What this means is that now we can have another action potential. Of course, we're going to need a super threshold stimulus, which means a stimulus that is greater than the 10 to 15 millivolts that we needed for the initial threshold stimulus. We're going to need something greater than that. And so this is going to be known as our relative refractory period. And this one over here, from threshold to threshold, is known as our absolute refractory period. So now, coming back to second threshold, we have those voltage-gated potassium channels closing, but remember they open slowly, so now they're going to close slowly. And because of that slow closing, this is going to result in what we call hyperpolarization. So it's going to go even lower than that negative 65 millivolts that we had earlier. And what's going to bring it back up to the resting membrane potential is going to be those sodium-potassium pumps. So that's going to bring us right back up to resting membrane potential. Yeah. So now what I'm going to do is I'm just going to put these numbers and associate them on this graph. So you can see how these voltage-gated sodium channels and these voltage-gated potassium channels are actually looking during this whole thing. So up here, we can see that our activation gate is closed and our inactivation gate is open for the voltage-gated sodium channel. For the voltage-gated potassium channel, we can see that our activation gate is closed and there's no inactivation gate on the voltage-gated potassium channel. So this is going to be representative of resting membrane potential. So I'm going to put my 1 right there. The next one, 2, we have our voltage-gated sodium channel. The activation gate is open, and the inactivation gate is also open. So this is going to be representative of what's happening at our first threshold. And looking at our voltage-gated potassium, they're opening pretty slowly, but they are opening. Looking at number 3. Number 3 is going to be associated with the peak of depolarization. And that's going to be the closed inactivation gate and the open activation gate of the voltage-gated sodium channel. Of the voltage-gated potassium channel, we have the activation gate that's fully open now, allowing for that efflux of potassium. Now, that efflux of potassium is going to allow us to repolarize the cell, and when we get to second threshold, we have the configuration of this number 4. So what number 4 is showing us is that the voltage-gated sodium channels are going to have their activation gate closed and their inactivation gate open. The voltage-gated potassium, they're starting to slowly close. So now we continue to hyperpolarize because those potassium channels, those voltage-gated potassium channels, are closing pretty slowly. So then now we get back to number 5, which is the new resting membrane potential. We have the closed activation gate of the voltage-gated sodium channel, and the open inactivation gate of the voltage-gated sodium channel, and the closed activation gate of the voltage-gated potassium channel. So, yeah, that's pretty much it for the action potential. Thanks, guys.